All right. Good morning and afternoon, everyone, and thank you for joining us. My name is Kevin Murphy with the Office of Water Programs here at Sacramento State, and we're pleased to welcome you to the first of two spring 2026 Water Seminar Series presentations. For those who may be less familiar with our organization, the Office of Water Programs is a training and research organization focused on water quality and water resources. And each year we host two seminar presentations in the fall and two in the spring. And in keeping with that schedule, we'll have another presentation coming up later this spring. So please stay tuned. I'd also like to note that all our presentations are recorded and made available on the Office Water Programs website for later viewing. Today's presentation will run about 45 minutes, followed by 15 minutes of questions. If needed, we can extend slightly beyond 1 p.m. to address additional questions. If we're unable to get to them all, I will forward the remaining questions to Tom, who, if he has time, will respond by email. Please submit your questions by emailing them to seminarquestions@owp.csus.edu. You can take a screenshot right now of the address or refer to the chat. We'll send that out to the chat now and then, so you can use that email address. So it's now my pleasure to introduce our speaker, Tom Moles, who will be presenting on dam-related flood inundation mapping. Tom brings over 30 years of experience in hydraulic, hydrologic, and water resources engineering, having led and managed projects for local, state, and federal agencies. In 2021, he joined the California Department of Water Resources, where he currently leads the Division of Engineering's hydraulics section. In this role, he oversees the development of regulatory inundation maps for the state water project. Prior to joining DWR, Tom worked as a consulting engineer in Sacramento, served as an assistant professor at Southern Illinois University, Carbondale, and was also part-time adjunct lecturer here at Sacramento State. And with that, I will turn it over to Tom.
Hey, thanks, Kevin, and the Office of Water Programs for allowing me to talk about our inundation mapping efforts here at the Division of Engineering. I'm going to share my screen. I have two screens going on, so if I'm looking back and forth, it's not because I'm distracted. I'm just... Okay, can you see that?
Yes, looks good.
Okay, perfect. So I have quite a few slides, so I'm just going to get right into it. We're going to be talking about the inundation mapping that we've been doing here at the Division of Engineering since I got here for the last 5 years. And I'm going to, I'm going to try to stay, I don't want to talk at the 30,000 foot level, but I can't go all the way down to the ground. So we'll be around 5,000 feet. And I want to give you a feeling for how we develop these maps, why they're developed and how they're used. And in 45 minutes, I can hopefully can do a good job of that, but we can't talk about all the details. So there's some definitions that we have to go through initially, and then I'll talk about how we make the maps, what facilities we make the maps for, and then how the maps are used really. So we have to first start and understand what maps we're making. So, the Department of Water Resources is an agency, is a department under the California Natural Resources Agency. And it really has a broad mission, but it protects, conserves, develops, and manages much of California's water supply. There's other departments under CNRA. Most folks know the CAL FIRE, Parks and Rec, and DWR is one of those. But the important thing for us is that DWR manages this thing called the State Water Project. And the State Water Project is basically a storage and conveyance facility system for the state of California and also provides flood protection. But this system has essentially 36 storage facilities, reservoirs, and dams, pumping plants, power plants, and probably the most well-known item of the State Water Project is the California Aqueduct, which you see in a picture up there. But just to be clear, the State Water Project's not the only game in town in California. There's a thing called the Central Valley Project. That's a federally funded water conveyance and flood protection system. There's a thing called the State Plan of Flood Control, which DWR also manages. And there are many other flood and water delivery systems in California. We're talking about the State Water Project. So, and then there's two other things that you need to know as we progress through here, that if you own a dam in California, you're required to develop what's called an emergency action plan. That's a document that basically describes how you would address an emergency for your dam. And the thing that we're really interested in today is that in that emergency action plan, you have to have an inundation map. That inundation map would describe approximately what area would be flooded if the dam were to fail. And DWR owns and operates some dams in California. And there's about 20 of these dams that are what are called jurisdictional dams, for which DWR has to develop an emergency action plan and also has to have inundation maps for it. So just to quickly describe what we're talking about. So inundate, also referred to as a floodplain, an inundation area and a floodplain are kind of synonymous. It's basically, where the water is flowing. And I want to describe, FEMA actually has a very good definition. It's a regulatory kind of definition, but it's a good definition. It says any land susceptible to being inundated by floodwaters from any source. And one of the main reason I'm bringing this slide up here is that we're not talking about FEMA inundation maps. They're probably the best known inundation maps. They're used for flood insurance purposes, but if you try to submit a FEMA map for what we're talking about today, it's not going to work. So we're not talking about FEMA floodplain maps. There are many inundation products out there. We're talking about a specific product for inclusion in an emergency action plan, an EAP. So the maps that we're going to talk about today are what we call hypothetical breach inundation maps. So these maps describe the flooding area that could result from a hypothetical breach of a State Water Project dam or its critical appurtenant structure, which I'll tell you what that means in a minute. And the maps that we produce are required to show the maximum depth, the maximum velocity, and this thing called the arrival time, the 1 foot arrival time. So how long does it take for the flood wave to reach your location? And today, these maps are, you can print them out, but they're PDF files and they're also GIS raster products that can be served over GIS or the internet. So just so you know, like the agencies that are involved for the State Water Project inundation map effort, the Division of Operation and Maintenance, which is under the State Water Project, DWR, they're really the ones responsible for developing and submitting these maps. Also under O&M is what's called the Emergency Preparedness Branch, Those are the guys that are responsible for making the emergency action plans. And then I sit in the hydraulic section, and between us and the DOE geomatics branch, we develop and make the maps. And we give them to O&M, they submit them. Then under another group, another division under DWR is the Division of Safety of Dams. They do many things, but one of their missions, one of their tasks is to approve the inundation maps. So DWR makes the maps, and then there's a regulatory arm of DWR that reviews and approves the maps. And then there's a whole separate agency, Cal OES. They're tasked with reviewing and approving the EAPs, emergency action plans. And this is just adapted from DSOD's website, kind of see, there's a dam owner. In this case, it's DWR, but other folks own dams, entities own dams in California. The owner makes the map, he sends it off to DSOD. DSOD hopefully eventually approves the map. And by the way, today these maps are available on a public website that's served by DSOD. Well, those maps go into the EAP, and Cal OES approves those, and then the EAP is used and disseminated to stakeholders. So, why do we make a map? Well, the short answer is it's the same reason you have a driver's license, or it's the law. So if you are lucky enough to own a dam in California, you got to make an inundation map and you got to develop an EAP. And I kind of put this up here just for reference, but there's the way these laws get enacted is there's 24 California codes, they're called. So the Senate passes a bill. In this case, it's SB 92, which was passed in 2017. And that bill has language about emergency action plans and inundation maps in it. And that gets encoded into these 24 California codes. You can see all this online. And this section 6160 and 6162 state that you got to make a map and an EAP. And then, so those are kind of general guidelines. They just basically say you got to do this. Then there's this thing called the California Code of Regulations, and these are laws that are developed by state agencies. Basically, they're more specific rules for implementing the California codes. And those guidelines now tell you more information about how the maps have to be developed. And they actually reference some other engineering documents, which I've put down below here. And if I'm going to try this, it's dangerous, but I'm going to try it. I want to just see. So this is the whoops. Hold on. I probably broken my system here. Can you guys see? Are you seeing the presentation, or are you seeing the?
We're seeing the presentation with the slides off to the left-hand side.
Is that better?
Same. Now you have the notes off to the right.
Okay. I'm not going to do it. I was going to do that.
There you go.
Okay. So I was going to go off to the internet and show you where one of these are. They're very easy to find today. It's all up online, but I'm not going to do that. So what I did do is just kind of summarize. This is actually from the California Water Code, where you can see just give a flavor for what these regulations look like. It's telling you that if you're an owner of a dam, you're responsible for this emergency preparedness, and that means that you have to develop an emergency action plan. And then the next paragraph below there says, well, that emergency action plan has to have an inundation map. The CCRs will go into much more detail about, what that map has to have. So the first thing is that we have to do is define a dam. So there's a regulatory definition of a dam, and it's in that water code. And that 6002 tells you what a dam is, and that 6003 tells you what a dam isn't. And you put those two together, and you have this definition. So you can see that the dam has two things involved in it. One is the size for the definition, and the other is like how much water is in the reservoir that could potentially be released. And that makes sense. But you look 6 feet's not that tall, 25 is getting tall. What 50 acre feet of water. When I was doing this, I looked around, and a football field, 100 yards by 50 yards is about an acre, pretty close. So 50 acre feet is like one football field, 50 feet high of water, or 50 football fields, 1 foot high of water. So it's a lot of water. And if that water is trying to get into your basement, you're going to think there's a huge flood. But from the perspective of the State Water Project, 50 acre feet is not much. Like the smallest off-stream storage dams that we have are like 10 times that, 500 acre feet. Oroville is 3.5 million acre feet. So pretty much, every State Water Project dam is going to meet this criteria. The other thing is that this idea of a critical appurtenant structure. So the dam itself, the embankment has to meet this regulatory requirement. And by the way, if there's another thing that's saying there's a low hazard dam. So a low hazard dam is not a jurisdictional dam. I'll talk about that in a second. But a critical appurtenant structure, I had to look this up when I first started. It's a fancy word, but appurtenant means belonging to. So these are structures that belong to the dam that also, if they hypothetically failed, they could also produce inundation downstream. And so a CAS, it has to be 25 feet or taller, or it has to hold at least 5,000 acre feet of water. Or there's another clause there that if the department thinks it's a hazard. So for our purposes, these critical appurtenant structures are really like weirs, overflow weirs, spillway gates, or low-level outlets. And I'll talk about them in a minute. And then there's this idea of the downstream hazard classification. So if DSOD, deems that your dam is a low-level hazard, well, you don't have to go through this process. And basically, if you see it can't have a life loss associated with the failure, and it pretty much the damages have to be restricted to your property. Then it's a low hazard dam. So I'm talking about State Water Project facilities, but there's a lot of other facilities, a lot of other owners of dams in California. And so this is showing you that, there's about almost 1,300 of these facilities, and there's a lot of different entities that actually own and operate these facilities. And so these are the ones that we develop maps for. And there's 20 of them. See the Oroville Field Division, Delta, Southern Field Division. And there's 20 of these facilities, dams, but there's also some of these dams have critical appurtenant structures. So each of those structures has to have a map as well. So we talk about all this, but I'm just gonna use this as an opportunity to kind of show you a few of these facilities. So we'll look down south, a little bit north of 50 miles or so north of Los Angeles, the Pyramid and Castaic Lake, and Castaic Dam. So there's the dam, the embankment. That's this picture is skewed a little bit. That's the breach opening that we assume when the dam fails. I'll tell you how we do that a little bit, but it's symmetric really, but the way this picture is skewed, it looks a little bit asymmetric. So, we have to find a way, we have to breach that dam and then estimate the inundation area downstream of it. But you can also see that there's a gate, a spillway with a gate. So there could be water behind that gate. That gate is higher than 25 feet. It's like 30 something feet. It holds more than 5,000 acre feet of water behind it if it were to fail. So we have to make a map for that. And then there's a tunnel basically that goes under the dam so you can make releases. And that tunnel, that pipe has valves in it so that you can meter the flow out of there. But if that system were to fail, you'd have water shooting out of that 19-foot pipe or whatever it is. And we have to make a map for that because it's more than 5,000 acre feet sitting behind that. This dam also has an emergency spillway, which is basically a weir. It's an ungated spillway, and water could flow over that if there was a very large hydrologic event, a storm. But this weir itself is only like 4 feet high, and it doesn't impound 5,000 acre feet of water, so we don't have to make a map for that and put it in the emergency action plan. Just downstream from Pyramid Lake is Castaic Lake. This also has an ungated spillway, but this spillway actually is a CAS, and it's taller. It's like the structural height is like 9 feet, and it impounds more than 5,000 acre feet of water. So let me talk a little bit how we develop these maps. Um, Today we use hydraulic modeling software. It's really HEC RAS. Um, in order to develop the maps the way we do today, we need good terrain data. And fortunately, we have that. Over the last 10, 15 years, the availability of detailed terrain data has exploded. You can download good data off the internet. We have better than that. So with that terrain data, we use a hydraulic model to develop an inundation map. And then we send those rasters to our folks in the geomatics branch here at DOE, and they make the pretty maps for us using, ArcGIS. And, what is HEC RAS? Well, it's a hydraulic modeling software that we use. It was developed just down the road from Sacramento in Davis, California, by the Hydrologic Engineering Center. And today, starting about 2010 or so, all the maps we make are two-dimensional using the RAS 2D capabilities. And I'll talk about that in a second. So this is my 1D, 2D slide. So, you know, uh, the world's three-dimensional, but you can make assumptions, simplifications, and make your job easier. So back in the day, the first maps that were developed all the way up until about 2010 used one-dimensional modeling. And you can think of that as like cross-sectional based. Like the thing about a one-dimensional model is that you kind of have to the flow is restricted to that blue streamline. So it works very well in a river because that's the way the flow is going anyway. But when you talk about flow over land flooding, the water can go right, left, backwards, forwards. So it's much more accurate, it's better, and we have the computer capability today to develop two-dimensional models. So these are like mesh-based. So instead of a cross-section, you have a mesh, and the terrain, you need good terrain for that, but the terrain gets projected onto the mesh. And then the model computes, the two velocity components and the depth or water surface at each one of these mesh cells. There's also three-dimensional modeling called CFD modeling. We don't use that for inundation mapping. The 1D and 2D hydraulic models are basically birds of the same feather. One is a very natural extension of the other. The 3D CFD models are a little bit different. The main thing that's common between the 1D and 2D models is that you can solve directly for the depth. Comes right out of the computations. 3D model, you're really solving for the pressure. There's a whole other step in trying to you have to track the water surface because some cells are wet, some cells are dry, that type of thing. And today, you can run very large two-dimensional computer models relatively quickly. 3D models are still kind of the computing power is not there. You can't develop a three-dimensional model of the entire Central Valley and expect to run that anytime soon. So what kind of information do we need to develop these models? Well, we need the terrain downstream of the dam. We need to know something about the reservoir because that's the water that's being supplied. It's going through the breach and out onto the floodplain. We need to know something about the embankment, like how big is the breach going to be? How long does it take to open? And then we need to know something about the boundary conditions, and I'll talk about those later. That comes into what we call like a sunny day map or a PMF map. And we take that information, we incorporate it into this HEC RAS model, and then we run it, and out pops the raster, and that goes off to the GIS folks, and they make the map. So I'm gonna start like from a high level, 3 slides on how a map is developed. So I'll talk. I'm going to talk about a few different maps that we've made, a few different facilities, just as a way to give you, a tour of the State Water Project a little bit. I could just talk about like one, but we'll skip around a little bit. So this is basically the start of the California Aqueduct. Bethany Reservoir, water's pumped up into Bethany Reservoir from the Delta. And then from Bethany Reservoir, it gets pumped up into this smaller reservoir, Dyer Reservoir. And Dyer Reservoir is basically the beginning of the South Bay Aqueduct, which goes down through Livermore and supplies water that way. So let's look at this reservoir. So this is the terrain, and there's no hydraulic modeling going on here. This is just a depiction of the ground surface. So the better this terrain is, the better the model is going to be. And on top of this terrain, we put a mesh onto that, mesh cells, and onto the mesh gets projected that terrain. And then the model, what we also do is we incorporate hydraulic features into the model. So you see, should be able to see this. So this is a depiction inside the model of the reservoir itself. And I'll talk a little bit more about these features. Here's the embankment. This is called the hydraulic structure. Here's where the breach is going to happen. We can align the mesh to high ground to get a better solution. So we do all that, and hopefully we press run, and the model chugs away, and out comes the inundation map. And so today we use RAS to do 2 things. It produces the breach hydrograph, which I'm showing you here, the flow versus time that's coming out of the reservoir. And then that gets put onto the mesh, onto the grid, and the model routes that downstream. So that's the very high level talk of that. So let's just quick, I want to show you just a couple things to give you a feeling for how these models are developed and so what we might have to do as we're going through the process. So now I'm over at Oroville Dam. I'm not going to talk about too much of this because I have another slide that we can talk a little bit more about. But this Oroville Dam is a very large dam. It's over 600 feet high. It produces a very large inundation area here. So we have a lot of terrain here, and inside that terrain are some very large rivers. So we want to make sure that these large rivers have the terrain below the water. We call that bathymetry. So we have to come through here, and when this terrain is usually developed today by flying a plane over there. If there's water in this stream, in this river, you can't see what's underneath that water. So we have to come through here. There's several ways to do this, but what I'm trying to let you know here is that we have to make sure that we have a good terrain. And one aspect of that is to actually be able to have large rivers convey water properly. And, we put a mesh on that, and you can see what that looks like. So we need bathymetric information for if you have a little tow drain out somewhere, it's not that important, but something like the Sacramento River or the Feather River in this case, or the Yuba River, we include the bathymetry for that. The other thing is you can have features in the floodplain that are blocking flow and that shouldn't be. So this is an example of the Thermalito forebay. It's in the Oroville Thermalito complex. It's a reservoir just downstream of Oroville Dam. It sits between the Hyatt power plant and the Thermalito power plant, which is down here. So this is a regulated jurisdictional dam. So we have to make an inundation map for this. So we have a breach here, and right downstream of this breach, and there's a couple of these road crossings here that have culverts in them. So if we look at this, here's the breach. This is just the terrain from the RAS model. This is a creek, a stream here. And here you have a road, but this road is basically an impediment to the flow. And this breach isn't so big that, this impediment we want to put it into the model to make sure that we have reasonably accurate inundation area. So this is what it looks like, from a picture. There's actually a culverts underneath there. So water can go underneath this embankment, this road. And the way the terrain is right now, sitting here between A and B, there's a blockage. So I'm showing you that here, it's about almost 10 feet sitting up in the air. So what we can do, there's actually two ways to deal with this. One, today it's very easy in RAS to go in here and just kind of sculpt out an opening in this embankment. You can also have your GIS folks do this right into your terrain. But basically, you can take this elevation and just project it down here. And now there's a passageway through this embankment. But you can do better than that, and you can include a hydraulic structure in here, which is basically an embankment in the model. And then you can embed culverts into that structure. So this is the structure editor, and you can see here's the top of the road, and here's the culverts. These culverts get put in through a culvert editor, and now when the model sees this culvert, it's actually going to compute flow through that opening, that rectangular opening, using standard hydraulic equations for pressure flow or for weir flow, depending on how high the water is on this. So that's how there's, if you have a large model, if you have small culverts that really aren't influencing your inundation, you might not need them, or you can just kind of like open them up like I did before. If you have something that you think is significant, you need to include that in the model. So that's the terrain. There are other aspects of that, but I give you a feeling for how that is manipulated and included. So then we need information about the reservoir. So that comes in, there's multiple ways to do this, but that comes in through an elevation volume curve. So we know that, the reservoir has a certain capacity, but depending on how much water is in the reservoir, how deep it is, there's more water or less water. And that's all embodied into this, just a curve, just one curve, a reservoir elevation volume curve. So the elevation here is on the right-hand side, and here's the reservoir capacity. As the water gets deeper, there's more water in the reservoir. That's the water that's available to come out of the breach eventually. And this is a good picture of, Dyer Dam's small, so it can be dewatered. You can see what the reservoir looks like. And, as the water comes up, you just have more volume in there, and that's depicted in that curve. This is where the water comes in, pumped from Bethany. You can see like some trucks here. This is a small reservoir. So this is what it looks like in the RAS model. So there's this feature. It's called a storage area. Gets included, and all we do is just take this, and it's digitized. We just put these values in here, elevation and volume. And this hydraulic structure, this connection, it's connected, the reservoir is connected to this hydraulic structure. So if water is going to go through this breach, or if it were to flow over this thing, the model knows that these two features are connected. So what about the embankment information, the breach embankment information? So here we are at Dyer Reservoir still. Just want to give you a feeling for what the embankment looks like. This embankment's like 30 feet high, somewhere around there. And I couldn't find a picture exactly where we have this breach, but you can see what the embankment looks like. There's some riprap protection here. There's these men here. That's about where the breach is. So how do you include that into the RAS model? Well, before we included this hydraulic structure so we could put a culvert in it. Well, this time we have a hydraulic structure. It's connected from the reservoir to the grid, to the mesh. But now we're going to include a breach in there, into this hydraulic structure. And here's the information for that. So there's a breach editor. There's multiple ways to do this. The way we do it for this analysis is we use regression equations that kind of guide how the breach is going to evolve. So the most important things are like the final bottom width, the final bottom elevation. We assume a trapezoidal breach. So these are the side slopes and the breach time. How long does it take for this whole thing to open once the failure begins? And in those code of regulations, those codes of regulations that we talked about before, I showed you they're all online, they reference these other engineering documents. And these documents here have more detailed information and guidelines about these breach parameters. So like, for example, DSOD, if you produce an inundation map for DSOD and it has a breach formation time that's over 4 hours, they're going to ask for some backup on that. It's hard to know exactly how quickly or long a breach is going to take, but The general guidance is here. We have regression equations for that. You can also use physical computer models to try to estimate those parameters. And this is just show, I kind of showed this before, but this is a closer up picture, kind of showing you what the results are. The model has to compute the breach hydrograph. That's dependent on those breach parameters, and it's dependent on how much water is in the reservoir and how high it is initially. It passes that breach hydrograph onto the mesh, and then the model routes that based on solving the 2D equations. So just something to consider, it's hard to really know how long the breach is going to take to open. Is it 1 hour, 2 hours, 3 hours? So, for all these parameters in question, we do sensitivity analyses. And so this is the sensitivity analysis for Oroville Dam. And you can see Oroville Dam is the breach itself, the baseline breach is a 1 hour breach. That's what the map is made on. It goes into the emergency action plan. But you can see if you have a 1 hour breach, a 2 hour breach, or a 4 hour breach, the breach hydrograph looks considerably different. It's 38 million CFS to below 20 million. But 20 million is so big already that the difference between the actual inundation is not really significant. So the black area just shows you the difference between the 1 hour breach and the 4 hour breach. And the coloring here is telling you the depth difference. So, if you look at this bigger picture, all this area below here is basically the same inundation area, and it's less than 1 foot deeper for the 1 hour breach. There's, some local differences right downstream near Oroville, but the depth there is already so big. It's important to do these types of analyses, when you're developing the analysis so that you understand how these parameters affect the solution. So let me just talk about the boundary conditions a little bit. This goes into what we call a fair weather or a PMF, a sunny day breach. So really, there's three things that are important. One is like, what's the stage of the reservoir when the breach happens? How high is the water in the reservoir? And is there water coming into the reservoir? Like, is it a flood happening, or is it kind of maybe in the summertime, where there's not much water coming in? And then the other thing is how much water is downstream. So we call a sunny day breach, for these regulatory maps. We assume that the water is all the way up at the emergency spillway crest elevation, for these dams, and that there's really no water downstream and there's not much water coming in. That's a typical, sunny summertime condition. Then we have what we call the PMF condition, and this is a flood condition. So the water might rise above the emergency spillway crest because there's a very large storm happening. There might be some water downstream in the channels already, and there is water coming into the reservoir. These are two different scenarios. You can make maps for one or the other. We make both. So this is a picture just to give you an idea of a situation. This is pretty much a sunny day breach situation for Oroville. The water, this was just last year, 11 months ago. The water is like just a few feet below the emergency spillway crest. That's being controlled by water coming out of the gated spillway so that it doesn't get above spillway crest. And so this is the 901. So when we make a sunny day map, we assume this condition. Now, every year this doesn't happen. So this is last year, this is this year, it's going to get close. But 4 or 5 years ago, the water was way down there. But for the regulatory map, we assume that the water is up at 901 feet. This is just a picture of, while we're talking about reservoir elevations, um, we have, I have 16 years of reservoir. The reservoir is measured every day since 1979, reservoir elevation. So you can see that it's not unusual for the water to get up to the emergency spillway. And a good year, it's there, and then it's operated to stay there. When we have dry years, it's down here. It's not unusual for it to be a lot lower. What is unusual for it to be average. The other reason I put this in here, it's kind of like timely today. This is 2000. This is what happens in the summertime is water starts to be released for environmental and human consumption. And this is 2011, 10, 11. That was a huge. There was a lot of snow in 2011, 10. And so, you're making releases here and water is still coming into the reservoir because the snow's melting. This year here, 2023, 24, the water was just about as high, at the end of the winter, but it's dropping down significantly here. There's two reasons for this. About two-thirds of this is because in 2010, 2011, there was about 1.2 million acre feet coming into the reservoir after June 1st. And 2 years ago, there was only 500,000 acre feet. And a little bit more was released too. But this is all due, but mostly two-thirds of this is due to snow. I'm kind of getting close. I have maybe 10 minutes. It's interesting, to look at, we have information, like I said, since 1979. It's easy to measure the reservoir elevation because all you need is a stick in the water and put some marks on it, and you have a staff gauge. And it's very accurate. So it's good information. If you know what's happening every day to the water surface elevation in Oroville, you also know what's happening to the storage because you have that storage elevation curve. We know how much water is coming out of Hyatt. It's the power generation. If you open up the spillway, you know how much water is coming out of there. You can basically calculate just with the continuity equation, flow in, flow out, and the change in storage. You can calculate how much water is coming in to Lake Oroville every day. There's no modeling. You don't have to worry about infiltration or snow or whatever. It's just the water that came in. And you have this database, you can just sum this all up. You can aggregate it for every year. So that's what I'm showing here. This is from 2010 all the way to just 2 years ago. You can see the variability in the actual water that's coming into the reservoir. That's just the way it is. And we have this data since 79. You can see, if 1 million or 2 million CFS comes in or acre feet comes in for a year, that's not good. You're going to call that a drought. The water is going to fall in the reservoir. If 6 million comes in, it's good. We can produce these types of graphs as well. This information this is focused on flooding. It shows the years that the gated spillway was open. And I've aggregated put some information on this plot. So the famous 1997 water year, there are 130,000 CFS. That's the 1 day flow out of the spillway. 52 days, the spillway was active. That peak happened on the 1st of January or 2nd of January. And this 2.6 million acre feet was released. And this tells you how much came in that year, 6 million. So we have this kind of information. It's just interesting to look at. So let me quickly go through. I'm about done. I want to just show you what the final product looks like for these maps. This is where our geomatics folks come in at DOE, help us with this. So we have a map for each critical appurtenant structure. This is for Castaic Dam. This is a good one to show just because it fits on the slide well, and it's contained in then it has a lot of overland flow down by Oxnard. So for each one of the scenarios, we develop a depth, a velocity, and an arrival time. And the maps, so this is Castaic, we saw this already. The maps themselves have a cross-section table. So we provide information kind of tabulated up at various locations in the floodplain. We have, an overview map, and then we have these detailed panels. There's a legend, there's notes to describe the information that's in the cross-section table. So this is the depth. It looks exactly the same, except this is colored with velocity. So you're looking at velocities. This is colored with the arrival time. So you know that this wave takes 2 hours to get down halfway to Oxnard. It takes about 4 to 8 hours before it comes out onto the floodplain there. So this is what a detailed sheet looks like. And here's the cross-section table. This is a detailed sheet down halfway down the floodplain. Now it's colored with the velocity. Here you can also see, part of the GIS process is getting these data layers. So we know where the fire stations are, police stations, so you can see if that's in the inundation zone. And now you're down in near Oxnard. This is just showing you the difference between the peak flows for the main dam, which is like over 5 million, and the appurtenant structures, which are down at 25,000. Obviously, the inundation looks different for those. And we have one of those regulations says you got to have an engineer stamp the map. DSOD won't approve it without that. And these maps are made available to the public. So this wasn't done before 2017. Now they're made available to the public. And you can go onto DSOD's website and pull up a map. That's Oroville. And finally, these maps they only go into emergency action plans, but they're also used for the risk informed decision making. So if you have an inundation map and you know where the structures are, you can place those structures in the inundation area, see how many people are affected. You can estimate consequences like damages, can estimate consequences associated like life loss, that type of thing. And DWR does that and to prioritize, projects. We look for projects that are going to have higher consequences to do first, and focus on it. And there's a whole risk-informed decision-making process associated with that, and these maps are used in that process. I want to just very quickly, I got about maybe 3 minutes here. Just so you know, the inundation maps that Senate bill was 2017, but DWR has been making inundation maps since 1973 were the first maps. And by the way, pretty much the entire design and analysis for the State Water Project that was done back in the 60s and 70s sits right here in these shelves. It's a pretty amazing resource. You can go back and you can open these up and you can look. There was a Senate bill. It's not 92. It's got a different number on it, but it's got a lot of the same language in it. Back then, the maps were developed by hand calculations, because there were no computers. So that was the big computer of 1973. So it's interesting to go back and look at this. The entire the State Water Project was designed, analyzed, and built without a computer model. When you think about that today, it's kind of makes you think. This is the modified pulse routing, how they got the flow from the breach downstream. And this is, I couldn't find a 1973 paper map anymore, but this is the most recent, the oldest one I could find. Compare it with our current map. This was developed with a 1D hydraulic model. The one on the left, it's late 80s. Not too different. This is the Feather and Sacramento River here, so you could see the kind of get your eye oriented. And that's the end of my talk. I think I went a little bit longer than I'd hoped, but I would like to say, that some of these images that you've seen, I was at HDR and David Ford Consulting when we were making those. Since I've moved to DWR, making them here, but some of the images were from projects that I did previously.
All right. Thank you, Tom. I have quite a few questions that came in, and I will just read them to you.
Sure.
All right. This is a great approach for proactive management relative to O&M and engineering. Was this process used to help reshape dam inspection, front-end engineering design processes, and condition-based maintenance strategies?
Yeah, the place that these inundation maps are used primarily for that is in the risk decision-making process. So I talked about that I showed that matrix there. The There are workshops that are involved that O&M puts on where you look at the dam, you look at the appurtenant structures, and you postulate things that could happen that would produce a consequence downstream. And so we use these maps for that process to actually estimate those consequences. And that whole risk-informed decision process it drives a lot of the projects that are hatched out of O&M. And we don't only use these maps, but a lot of times we'll use the models and make additional maps for those risk workshops for scenarios that aren't shown here.
All right. Thank you. Okay. Next question. Can this technology be applied to specific locations, specifically a particular city or county?
Yeah, this process, I'm kind of focusing on state water project facilities, but this the general inundation mapping process and analysis here could be, I mean, you could do levee, it could be for levee breaches. It could be for, it doesn't even have to be for a breach. It could be for some kind of flood-driven inundation. And a lot of counties and cities and other agencies had flood warning systems. They're doing this type of modeling to inform those flood warning systems.
All right, thank you. How do you deal with the possibility of levee failures downstream of a dam that has failed? Seems like a tricky problem because the levees might be in variable states of repair, i.e., they might wash away at spots if overtopped.
I knew someone was going to ask this. So that is a difficult issue. So what we do for these maps is, like, for instance, for the Oroville map, you see, we have a large portion of the Central Valley from Oroville down through Sacramento is in the inundation area. And so that map, and it's clearly stated on the map, it's in the report, is based on the assumption that downstream levees don't fail. They overtop but don't fail. And so, like, near Oroville or Yuba City, that really doesn't affect the inundation because the flood wave's already 50 or 100 feet high or more. You can get into situations where you're farther downstream and you can assume a levee breaches anywhere you want, and it's going to change the inundation area. And we do those sensitivity analyses for areas that we think are potentially sensitive to that. But you have to remember that these maps are for go into emergency action plans, and they're for emergency action planning, which folks could be under duress when they're trying to make decisions and such. So we can't give them, 100 different maps with 100 different scenarios for them to sort through. This map that goes into the emergency action plan is kind of to get you oriented, get you a good feeling for what might happen, and it's a starting point.
All right, this next question is pretty technical. It's has to do with height versus time and flow versus time. It appears that the maximum Q coincides with the gradient, the negative of the gradient of the HT curve. Is this a coincidence?
I'm not really sure what the question is getting at. If it's the breach hydrograph or
Yeah,
downstream.
yeah, it says the selection of breach time should affect the relative placement of the two, max Q compared to HT.
Yeah, but I could maybe take that offline, but it
Yeah,
but it is, I mean, it is true that the breach parameters affect the breach hydrograph, and there's you know today that's modeled within HEC RAS. So there's an accounting, a volume accounting for, as the breach opens, more flow comes out the breach, and that means more water is coming out of the reservoir, so the reservoir starts to come down. And usually the peak, depending on how fast the breach is opening, but if you have a breach that's opening 1 hour or 2 hours, the peak breach flow is going to be around when the breach reaches its maximum size, a little bit
but
after maybe.
so Tom, I'll forward you that question.
Okay.
It's from someone who's teaching themselves HEC-RAS.
Okay.
So he says your analysis helps. All right, next question. Uh, gathered these questions along the meeting. For for the arrival time, how do you quantify the arrival time when you investigate concurrent flooding conditions? Areas that are already inundated greater than 1 foot prior to the structure breach during a rainy day scenario.
Yeah, so there's actually tools now in HEC RAS for that. So there's an initial, the way we deal with so for the sunny day case, when there's hardly any water on the floodplain, there's no problem. But if you have water on the floodplain, the arrival time is going to depend on the arrival time from the breach. So typically, when we do a PMF scenario or a rainy day scenario, we we res we restrict the amount of water on the floodplain to be within the major channels, so that it's not all over the downstream floodplain. And then we have an initial water surface elevation associated with um, the antecedent flooding that's happening before the breach. So within HEC RAS, we can report the breach time from when the breach happens. It's incremental above the water that's already on the floodplain. So if the water is already 10 feet deep somewhere and you breach and it becomes 20 feet deep, that breach time is the time after the breach happens.
All right. And second part of this question, how do you address slash communicate the uncertainty that comes with breach parameter estimation and general accuracy of breach models?
Yeah, so I mean, there is a lot of uncertainty in that. We have these regression equations that give us some guidelines, but the best way that we do that is through the sensitivity analyses. Like for instance, like for Oroville, I mean, folks love to talk about the breach parameters, just like they like to talk about Manning's N and such. And we do a sensitivity analysis for Oroville, and we show that it really doesn't make a difference between 1 hours and 4 hours, at least at the level that these maps are that we're interested here. And that's the best thing we can do um, it for these types of applications.
All right. Has anyone dared to ex post facto model the infamous William Mulholland March 1928 dam failure near
I
Castaic?
think I think so. I think I've seen information about that.
All right.
I have.
Uh, how do the old hand calculations compare to Heck-Raz modeling?
Well, it's interesting that so those calculations they're based on different guidance at the time. So even like the breach parameters are different, but those initial 1973 calculations, 73, 75, they're basically just a an exercise of using RAS, the and not RAS, the Manning equation. So those hand calculations are done. The breach hydrograph is done by hand. It was assuming they used the Manning equation for that, the 1D Manning equation. For the routing, they use modified poles with Manning's equation. To get the arrival time, they used Manning's equation. So it was all just at the time that's the best they could do. And by the way, I was thinking about that when I was looking through that. I and it's not because I'm smart or something, but for 30 plus years, Gary Bruner and his friends over there at HEC have been developing the RAS model, and now we have computer power. I could do all of those inundation maps that are in that binder there probably in like 2 days, and I could do a better job because I have RAS. So it's just interesting, but you know, it it took them, I don't know, months or a year to do that. But if I was going to do that to today's standards, it would also take me a year. So it's the work kind of grows with the technological capability. So
All right. Thanks, Tom. How frequently are these maps updated?
that's a good question. So the guidance is that, or the law there is that every 10 years they have to be revisited. But that doesn't necessarily mean that you have to produce and you have to update the emergency action plan and such, but that doesn't mean you have to make a brand new map potentially. If the downstream population hasn't changed much and you already have a good inundation map, you could potentially just do it like a GIS update where you put the new locations of structures and emergency locations, buildings, hospitals, and that type of thing. But they have to be kind of reviewed every 10 years.
Does or is sediment transport considered during dam breach?
Not in these the models that we have here. What we do well, and by the way, like the DSOD would rather have you include the like for instance, we use all the original elevate storage elevation curves for this modeling, and that means we don't account for potential sediment that might have come into the reservoir, which would potentially reduce the volume that's coming out. We use the original design, so it's a little bit it's conservative. And well, the one thing that we do is that we increase the friction in the model, Manning's End, immediately downstream of the breach, for a couple thousand feet to kind of account for, you know, sediment and just the energy losses associated with. That doesn't really make much of a difference unless the breach itself is pretty small.
All right. There's just a few more. Are you okay, Tom, with going a little bit
Yeah,
longer?
Yeah,
Okay.
sure.
When you say EAPs are available to stakeholders, who are the stakeholders?
Um, I'm not the EAP expert. That's David Panek here at DWR, but those stakeholders are like usually government agencies and such that are in associated with that facility. Like it could be cities, counties, sheriffs. Um, I don't know all of them, but I took David Panek's EAP seminar class. I should know that, but
Okay. When DSOD reviews inundation maps, do they have to perform their own HEC-RAS modeling and then compare the inundation maps?
no, they have another 2D model that they use to kind of make a quick check, but they'll usually they'll look at the report, they'll want to look at the rasters, the actual inundations, and if they have further questions, they're gonna request that you send them your model.
Okay, last question, unless someone sneaks one in. Um, let's see, Lake Oroville had some spillway and emergency spillway issues a few years back. And the Glen Canyon Dam during the Epic 82-83 runoff event had issues with the rock tunnels that operated as spillways. Can you comment on if dam failure or appurtenant structure failures are more typical?
Well, that's not really my expertise. And when you start talking about, I know when to stay in my lane. And
Right.
but yeah, but the short answer really that's I mean there are professionals that's their whole thing, is dam failures and the forensics of that. Um, and those are usually geotechnical types of engineers, and I'm a hydraulic engineer.
Yeah, that makes sense. All right. Well, great. Thanks, Tom, for addressing all those questions. And on behalf of the Office Water Programs and all of today's participants, thank you for both volunteering your time and delivering such an informative presentation. And we also appreciate everyone who joined us today. Have a
Yeah,
great weekend, everyone, and take care.
thank you.
Thank you.